All right, number 26 is a little bit of a tricky question. We're dealing with seismic waves traveling from an epicenter of an earthquake. It gives us a little bit of information, and we have to determine a couple of things. First off, we have to know or find out when the earthquake occurred. That would be also called the origin time. And we also, in this case, have to figure out when the S wave arrived, as is indicated by some of the answers here. Now, first off, realize that if the P wave arrived at 7:10 p.m., the earthquake origin, or the time that it actually happens, has to be before that time. It can't be after 7:10. So it's got to be a number before that. So we can get rid of number 3 and get rid of number 4 because these origin times are after. So that doesn't make any sense. We want an origin time of before, which 7:03 makes sense for both of these. Now, the next thing we have to do is figure out, okay, when does the S wave arrive? How many minutes after the P wave does the S wave get there? And in this case, if you kind of look at the number here, it's 2 minutes and 40 seconds after. Okay, I'm just going to write that down, 2 minutes and 40 seconds after. This one, it's 5 minutes and 40 seconds after. Now that's important because we're going to need to know that, and we're going to go to our reference table, specifically page 11, to figure this out. So let's go to page 11 and take a look at this page. Now, this would be a really good one to use scrap paper on. As you can see on the chart here, there is a distance at the bottom, and the distance given to us in this problem is 4,000 kilometers, and that is right here on the bottom of the chart, 4,000 kilometers. All right, now that I've found the 4,000 mark on the x-axis, I'm going to take a piece of scrap paper. I'm just going to draw a yellow box here to represent some scrap paper. And I'm going to take that scrap paper and I'm going to drag it right over to where the 4,000 line is and line it right up with my edge of the paper on that line. And then what I want to do is I'm going to mark where the P wave crosses my paper, right there, and where the S wave crosses my paper, right there. And then I'm going to drag the paper on down to the y-axis all the way down to 0, so my bottom mark is at 0, and then I can look right here and I'll read this off and it looks like it's 5 minutes and 40 seconds. Okay, so that helps us because that is basically the lag time. That's the difference between the P wave and the S wave. How many minutes later is it? 5 minutes and 40 seconds. So let's go to our choices. As you can see, the answer has got to be number 2. Okay? Alright guys, this question number 27 is another reference table question. Specifically, this is page 1. It's right at the bottom of the chart of your reference table. We're looking for the percentage of by mass, and that's key, by mass in Earth's crust. Okay, so let's go to our reference table on page 1 and take a look at that. Here we have all the chemical composition of the Earth's crust, and specifically we're looking for the crust by mass. So right there, by mass, and we're looking specifically at oxygen. Oxygen is 46.10, silicon is 28.20. So let's take a look at our graphs and check out what our possible answer is. The answer has got to be number 1 because, as you can see, oxygen is 46.1 and silicon is 28.2, and then there's some other that we didn't calculate, but that's the only answer that makes sense. So the answer is number 1. All right, number 28. This is a question that just requires some memorization here. We're talking about a hill that's made by glacial deposition. And so you can eliminate sand dunes because sand dunes are not made by glaciers. All the other ones are made by glaciers, but the one that this looks like, you can kind of see this elongated shape, the elongated hill as it says, that's got to be a drumlin. And that's just a memorization thing. Know that that really long, drawn-out hill like that is a drumlin. It's got a steep side over here and a more gradual side over there, and that actually points in the direction that the glacier moved. The glacier moved from this side over here to over here on the right-hand side of the picture. Most likely, the orientation of this picture, this would be the north side over here, and that would be the south side, most likely, because the glaciers came from the north and moved to the south. So you might see some other questions related to drumlins, but that's how you answer that question. All right, number 29 is kind of related to the previous question. This one's also about glaciers, but specifically we're looking at valley glaciers. up in the tops of mountains. And you have to just memorize this. Glaciers make U-shaped valleys, and so you can get rid of 3 and 4. Glaciers make U-shaped valleys, streams make V-shaped valleys. So the other thing that's true about glaciers is the sorting of their sediments. You would expect that the glacier would just drag all the sediment along the sides of the valley and scratch up and break down the bedrock. So you would see the scratched and broken up bedrock, and it would be completely unorganized, not sorted in any way, not rounded like a stream. So that makes the answer number 1. All right, number 30. Number 30 is a reference table question as well. Specifically, this one's referring to sedimentary rocks, so that's page 7 of your reference table. We're looking for bioclastic rocks. Remember, bioclastic means life fragments, right? Pieces of old ancient life that have been crushed and smashed together. So we are looking for an element that is always or almost always found in bioclastic rocks. So let's go to our reference table and take a look at that. Here's the sedimentary rock chart at the top of page 7, and bioclastic rocks are here at the bottom of that chart. So let me just circle that. There's bioclastic. The composition of bioclastic rocks, as you can see here, is carbon, compacted plant remains, right? So it's made from carbon, and therefore the answer to this question is simply number 3. All right, question number 31. What are 2 major factors that control the development of soil? Soil is controlled by a bunch of different things, but particularly it's all about the climate. Climate will affect whether soil will form or not, and therefore you kind of look for that choice. You want to look for climate, and there it is. There's one of the answers. That makes number 4 the correct answer, but it also, the bedrock composition, what is the bedrock made from? Because really we're talking about weathering and breaking down the bedrock, and that composition will kind of factor into whether soil will form or not. Climate kind of controls whether weathering and erosion will occur really quickly or not. If you have lots of precipitation or if you have warm temperatures, then you tend to have more soil formation. So the answer is number 4. All right, question number 32. This was a real challenging one. I remember staring at this question for a good long time, trying to figure out the proper sequence of events that occurred between what's the form that's called the Cambrian limestone and the Silurian limestone. So specifically, we're really looking at this line, this wiggly line right here. And if you guys remember, that's called an unconformity. It's a gap in geologic time. Unconformities are formed by the processes of weathering and erosion, and usually it's in that order. When I say weathering and erosion, I always say weathering first, followed by erosion afterwards, and that's because you have to break it down before you can really transport it really easily. So weathering is breaking down, then erosion takes it away. So if you look at our choices here, first off, you can almost eliminate choices because some of them have weathering and erosion in the wrong order. Get rid of number 4 for that reason, and get rid of number 2 for that reason. It just doesn't make sense to be the opposite, okay? Now, let's deal with some of these choices and just think about what's going on here. All of these bottom sections, all of these rocks that are here, especially the limestone, the shale, right in the Cambrian section, these are all sedimentary rocks that are probably formed underwater, right? In order to weather and erode something, it has to be above water. So it has to be lifted up above water, and then you can weather and erode it. So when we say lifting up, another word for that is uplift, right? Just reverse the words. So we uplift it, we weather it, and we erode it. We take some of the sediment away. You can see that it's like wiggly and all this stuff has been moved somewhere. And then in order to form this Silurian limestone on top of this, we basically have to put it back underwater again. We have to be in a marine environment for that to occur. And so you would have to essentially drop the elevation of that region down. We call that subsidence, where it sinks down below the water again. Okay, so the proper sequence is uplift, followed by weathering and erosion, followed by subsidence. So the answer is number 1. All right, guys, question number 33. This is a question about the composition of rocks, and specifically we're looking for the mineral quartz to be in this rock or in both rocks. And that just makes this a little bit challenging because you have to go through all of the choices to figure this one out. We're going to look at a reference table, pages 6 and 7 for the answer to this one, but you really do have to just go through all of them to determine whether it has quartz in it. So let's start with gabbro and schist. Gabbro is an igneous rock, so I'm going to take a look at the igneous rock chart, which is on page 6, and I'm looking for gabbro. So I'm just going to go down from gabbro. Here it is right there, and if I go down from there, these are all the minerals that are in gabbro, and as you can see, there is absolutely no quartz in gabbro. So we don't even have to look at the schist answer because it's not even a possibility. So we're going to cross out number 1. Okay, the next one, dunite and sandstone. Well, dunite is another igneous rock, so I'll stay on the same chart. Dunite is right here. It's a little bit hidden over there. But if you go down from it, you'll see that the only mineral in dunite is olivine. So that basically eliminates that choice too. So we're going to cross out number 2. All right, granite. Granite is another igneous rock. We'll stick on the same chart and check out whether it has quartz or not. Granite is over here. There it is. I'm going to go down from there. Does it have any quartz in it? Yes, it does. So we have to check the other possibility. And the other possibility, I already forgot. The other possibility was gneiss. Gneiss is a metamorphic rock. So let's go to the metamorphic rock chart on the next page, page 7. Gneiss is right here. Under metamorphic rocks. It's at the bottom of the foliated rocks. So let me circle that right there. Let's see if it has any quartz in it. If we come over to the other side, we can see the composition is all of these minerals right here, and one of them, as you can see, is quartz. That's got to be the answer. I'm not even going to check the last one. You could do that if you want to, but I just know now that that is the answer number 3. All right, number 34, a little bit of a tricky question, not terrible. You have to use your reference table, page 16, the back page. This is all about minerals, and we're specifically looking for a mineral that has fracture, not cleavage. But it gives you the formulas for them rather than the names. That's what makes this a little bit tricky. So I'm just going to go through my choices and see if any of them have fracture. We'll start with this first one, magnesium, silicon, oxygen, and an OH tagged on the end there. That's kind of a complicated formula, so let's try to remember that one. I'm going to try to find that on my reference table, MgSi4O10, and that is right here at the top of the list of the non-metallic minerals. It's called talc. Now let's see if talc has fracture or cleavage. Well, in our chart over here, here's cleavage on the left, fracture on the right, and as you can see, talc actually has cleavage. So that can't be our answer. So let's go back to our choices again, get rid of number 1. NaCl, if you guys know, that is the formula for a mineral on our reference table. NaCl is right here. It's halite. That's table salt. And as you probably know, table salt comes in those little cube shapes, and it has cleavage. That's not our answer choice. So let's cross out number 2. Now, CaCO3. You might know the formula for that one, and maybe that's a familiar mineral to you as well. CaCO3 is right here. That's calcite. And calcite, as you can tell, has cleavage as well. And unfortunately, we had to go through all of our choices to recognize that FeMgSiO4 is our answer. And therefore, I'm going to circle number 4. Now, just to confirm that, FeSiO4 is down here, or FeMgSiO4 is olivine. Olivine is right here on the chart, and that has fracture. So just to confirm that, the answer is definitely number 4. All right, question number 35 is, again, another reference table, page 16 question. We're dealing with minerals again, and this one's really quite simple because it's asking for what is in your pencil, probably the thing you're using to do this right now. So you probably know that you use graphite in your pencil, and if you didn't know that, you could always look on your reference table. Graphite is at the very top of page 16, and as you can see, it's right here, and it tells you that graphite is used for pencil lead. Okay, so the answer is number 2. All right, guys, we've made it to part B1. Part B1, questions 36 through 50 are all they're multiple choice questions based upon diagrams, pictures, so you'll have multiple questions all related to the same picture or diagram. Now, questions 36 and 37 all have to do with this nice graph of tides located at Kings Point, New York. And it's a good idea to read the description ahead of the actual question. And this is a 3-day period of tides, and as you can see, it just goes up and down and up and down and up and down. We'll get to that idea in a second, but let's just deal with question number 36. It's asking for, when does the first low tide appear on December 26th? Now, right here is December 25th, Christmas, but the next day would be December 26th. So essentially what we're going to do is pretend like we extend this graph out into the future. What would it look like? Well, it probably would go down and then come back up again and then go back down and so on and so forth forever. So we want to know, what time is this first low tide? In other words, right here. Well, the way to do this is to figure out, okay, how long is it between low tide? So how long is it between here and here, or from here to here? The time difference between these, as you can see, is approximately 12 hours. It's not exactly 12 hours, but it's close enough. And that's all we really need to know. So we're going to assume, going into the future, 12 hours would bring us to the next low tide. And what time would that be? Well, this is 6 p.m. right here, so 12 hours into the future would be 6 a.m. the next morning. So the answer to this question is number 1. Now, staying with this question, or this graph, the next question, 37, says, these Long Island tides show a pattern that is what? Well, as you can tell, this is definitely cyclical. It's up and down and up and down and up and down, a regular pattern. And as we just did in the previous question, we can easily make predictions about this and know what's going to happen into the future because it's so regular in its pattern. So the answer is number 1, cyclic and predictable. All right, questions 38 through 41. I'll start with number 38. It's a great idea here to read this paragraph because it gives you some information that's important to the next question. So as it says here, aphelion is Earth's farthest position from the sun. And that's important because the next question says, when or what season in the northern hemisphere is that? Well, it actually tells you right in the question, that's around July 4th. So you don't even really have to analyze the diagram for that because you know July is in the summertime. So even though we're really far away from the sun, it's still summertime in the northern hemisphere. And remember, seasons have nothing to do with our distance from the sun. It's all about our tilt away from vertical, which we're going to get to in a second. So that's number 38. All right, question 39 related to this diagram as well. I think it's wise to, just like number 38, label these letters that are on this chart. Obviously, we just found out that letter C represents summertime in the northern hemisphere. So I'm going to label all of these according to what season it is in our northern hemisphere. After summer comes fall, and you can just follow the arrows around. This would be winter, and over here at letter B would be spring. Now, that's important because if you analyze question number 38, it's asking for specific times when the sun's vertical ray moves from the equator southward to the Tropic of Capricorn. And if you remember, the Tropic of Capricorn is in the southern hemisphere. And if the vertical ray is overhead at the Tropic of Capricorn, that means it's the southern hemisphere summer. Okay? So if we know that our position is going from some point at which the sun is overhead of the equator, either spring or fall, to the southern hemisphere summer, that would be the northern hemisphere winter. And so we're looking for our last letter to be northern hemisphere winter, which we just realized was A. So really, in our diagram, we are going from right here, where the sun is overhead at the equator, and you can kind of see that it's shining on the equator. And then as we get over here at A, the sun is shining overhead at the Tropic of Capricorn, which is down here in the southern hemisphere. And so the answer to this question is number 4. That is definitely a trickier one, and you have to remember what marks the seasons and where the sun is overhead. So that just makes that question kind of difficult, but hopefully you can kind of figure it out with all the clues that are there. All right, number 40, approximately how many times does Earth rotate as it moves in its orbit from position A back to position A? So essentially, we're taking a full path around the sun from position A to position A. We call that a year, right? And so this is just asking how many times does Earth rotate in 1 year. And remember, one rotation is 1 day, right? So that would be 365 days in a year, and therefore it rotates 365 times as it goes all the way around that chart. Okay? Now, question number 41 asks, what is the tilt of Earth's rotational axis relative to a line perpendicular to the plane of Earth's orbit? And that sounds all complicated and everything, but basically all it's asking is, how much is Earth tilted on its axis? And you just have to recall this one. The Earth is tilted on its axis, not so much, it's just a little bit of a tilt. So there's the equator, this is the tilt of the Earth, okay, and it's tilted 23.5 degrees from vertical. The answer is number 2. That's just one of those questions you have to memorize. Know that the Earth is tilted 23.5 degrees. That's what makes us have summer and winter and spring and fall, and it's reversed in the northern and southern hemisphere. All right, questions 42 through 44 are all based upon this map of Doppler radar image of the eastern part of the United States. As you can see, there's definitely some cloud cover shown there. It's probably pretty stormy along this line. You can almost see a line that represents the front going right through here. Most likely this is a low pressure storm, probably a cold front, but it's kind of hard to tell exactly. But anyway, this first question, number 42, is asking about the surface wind circulation around the center of this storm. And remember, stormy weather tends to be low pressure. Okay, so low pressure, you have to kind of recall the relationships of weather to low pressure. Low pressure, lousy weather. Low pressure, if you remember me doing this, low equals converge, which means all the winds are going to be blowing in towards it. And that actually helps us answer this first question, because the winds have to be blowing inward or towards the center of the storm from high to low. So get rid of 3 and 4 because those both say outward. We want inward blowing winds. And if you remember, with a low pressure system in the northern hemisphere, United States, it's going to rotate counterclockwise. And that's just one of those things you're going to have to either memorize or just know, because it just requires your memory of what we talked about with weather in the classroom about low and high pressure. Now, number 43 is a question that's asking about, how do you know that it's windy on a weather map? High winds on a weather map would best be indicated by what evidence? Well, cloud cover of 100% does not really indicate anything about our wind. Okay, so you can get rid of number 1. Temperature and dew point values, actually type of precipitation, whether it's snowing or raining, that doesn't really tell you whether it's windy or not. You can have windy conditions in rain and windy conditions in snow. Doesn't really help us there. But let's take a look at the other choices. Temperature and dew point values, would that help us understand wind? No, that would just help us understand humidity. The best answer for this question is number 4. And remember, where the isobars are drawn close together, we have a high pressure gradient. The winds are going to blow really quickly. The air is going to want to move from high to low really quickly across that gradient. And so the isobars drawn close together is the answer. All right, the last question, number 44. As this storm system follows a normal storm track, it will most likely move which way? Well, you guys all know that storms move from the west coast to the east coast. So from west to east. So we would expect it to move east, but specifically, we either have southeast or northeast. So let's get rid of 4 and 2 to begin with. And let's actually analyze your reference table for an answer to this question. This is from your reference table. And specifically, I forget the page number. Here it is. It is page number 14. Let me just write that down so you know. Page 14. Okay, and we're looking at this chart called, sorry about that. We're looking at this chart called Planetary Wind and Moisture Belts in the Troposphere. And so we're going to zoom in on the United States. And remember, the United States are located between 30 degrees north and 60 degrees north. And so we're in this little belt called the southwest winds, which means the winds come from the southwest and blow this direction, as you can see by the arrow, towards the northeast. And so we would expect the storms to move across the country and mostly move towards us, towards the northeast. And so the answer to this question is number 3. All right, questions 45 through 48 are all based upon the little passage below about the Crete earthquake, as well as the diagram that's given to you in that region of where the earthquake occurred. So good idea to read the paragraph and analyze this diagram. You'll notice that there's some plates and some plate boundaries that are located on this chart, and those are all associated with your reference table, and specifically page 5. So I'm going to write that down and I'll show you what that page is. Here's page 5 of your reference table, the tectonic plate chart. And specifically what we're looking at is this region up in the Middle East. So we have a few plates interacting up here. It's kind of a complicated region. And so let's go back to the actual test. And I'm just going to write down that this is ESRT page 5, and you're going to need that for the next couple of questions here. So question number 45, which type of plate boundary is represented at point A? And let me just go back up to this. Point A is located right there, and you can see there's two arrows indicating the direction of motion, and they are kind of sliding past each other, as you can kind of tell there, which is kind of the hint to this. And if we look at our reference table, that region on our reference table, would be point A on our reference table, okay? And if you look down below, it actually tells you what that plate boundary is, and that plate boundary is known as a transform plate boundary. You can see the arrows sliding past each other, and that's actually the answer to question number 45. The answer is a transform boundary, where the plates just slide past each other. Very similar to the San Andreas Fault in California. Okay, so let's take a look at number 46. The names of the major tectonic plates X and Y. What are they? So if you look here, we have X at the north end of the map up here, and Y down here. We just need to figure out the names of those. And again, that's a reference table page 5 question. So I'm going to look here, and let me zoom back out again. We're specifically looking at the plate that's up here and the plate that's down in this region. And you can see this is the Eurasian plate, and down here is a plate that doesn't have a name, and that's what made this question a little bit tricky. You're like, well, there's no name here. What could that be? It's not the Arabian plate. So what plate is it? Well, the name is actually on the other side of the map, and you'll notice that this is actually Africa, and this is the African plate, and this is the Eurasian plate up top here. Okay, so we're going to go back to our question. The top plate, plate X, is the Eurasian plate. The bottom plate is the African plate. So if we go back to question 46, the answer has got to be number 1, Eurasian plate for X, African plate for Y. Be careful. A lot of people picked number 2 just because they saw Arabian on their reference table and they immediately jumped to that. So just be careful with that one. All right, question number 47. 47 is asking about what index fossils from your reference table are closely related to the corals that were radioactively dated in the study. So this is actually reference table page 8 and 9. Remember, that's the geologic history chart. And so we're going to go to that chart here in a second. But we're looking for an index fossil that would be related to corals. Okay, so specifically corals, and we're going to look for that on page 9. So let me go to the reference table here, and let me zoom out a little bit. Page 8 and 9. At the bottom of the page, you'll see a bunch of index fossils, but specifically we're looking for corals. And if you look here, corals are on this bar right there. And so we're looking at letters T, U, and V. And so if I go down below, T, U, and V are these names down at the bottom of our reference table. So these are those corals. And Lichinaria, Cystophyllum, Pleurodictium, those are all different types of corals. And so what I'm going to do is try to figure out those names and use those to figure out the answer to this question. So we're going to look for associated names, go back to the test, and let's take a look and look through our choices and see if we see any of those choices. It looks like number 4 is our answer, Lichinaria, Pleurodictium. Those are both types of coral, and that's how you answer question number 47. All right, one more. Number 48, which activity could best prepare residents along the Mediterranean coast to reduce the loss of human life during a tsunami? And remember, a tsunami is a large wave caused by an earthquake. And so we just have to kind of use common sense for these questions. You'll always see one of these questions on the Regents where they're asking about what to do in certain situations. Mostly use common sense, okay? You wouldn't want to board up your windows. That's not going to stop the water. Removing heavy objects from the walls in your home is not going to do anything. Okay, that would be good in an earthquake, but not for a tsunami. Plan evacuation routes to higher ground. That's the one that makes the most sense. You want to get away from the water. You want to get to higher ground as fast as possible, whether that's to the top of a building or to the top of a hill, preferably to the top of a hill. Building a reinforced basement is not going to do a thing, okay? You really want to think about getting to higher ground or planning an evacuation route to get to higher ground. So there you go. There's questions 45 through 48. All right, questions 49 and 50 are based upon this photograph of a sandstone erosional feature. So key thing here is realizing that this is sandstone and noticing that this is found in the southwestern United States. Looks like a desert-like climate out there. And that's helpful for answering question number 49, recognizing where this is and what would cause all of this erosion to occur. You know, that's completely sandblasted, as it said, taking out these like little parts of that sandstone feature. So what would actually do that? What would be able to like erode it like that? Well, it's not running water. It's on the top of a hill out in the middle of the desert. Can't be ice. That doesn't make any sense. Can't be the waves from the beach on the ocean. It's got to be wind. It's currently blasting away. The wind's picking up the sand and essentially eroding, weathering and eroding that sandstone feature there. The other question, number 50, is a reference table question, and specifically page 7 of your reference table, because this is a sedimentary rock called sandstone. We're going to look for sandstone to answer this question. So let's go to the reference table and take a look. There's the top of page 7, and sandstone is what we're looking at. And we're looking for the grain size of sandstone, which is made from sand, hence the name, 0.006 to 0.2 centimeters in diameter. And so we just go back to our test and say, okay, 0.006 to 0.2, that's number 2. So that's how you answer questions number 49 and 50.